So this isn't actually a graphing section. The graphing is 6.5. But that's where we're going to eventually. So, a couple definitions. A polar coordinate system is a plane with a point, and I'm just going to call that point O. The pole and a ray from that point O. And the polar axis. So, a visual of what this looks like. So this is going to be point O over here. This is the pole. This is the polar axis. You've got theta. And this is the point up here, r theta. Each point P is or I guess I should say in the plane, is a polar coordinate so this right here is a polar coordinate. Where r is the directed distance from O to P, and theta is the directed angle whose initial side.
Wait, is that O or theta?
Where? Right here or here?
There. Yeah, the same one.
This one is theta.
Okay.
Let's see, whose initial side is on the polar axis. And the terminal side is the line OP. So if you remember back from geometry, when you were calling like lines and stuff, like you would put whatever the two like endpoints of it were, and you would call it like OP for the like that line. That's what that name would be. Polar coordinates. Are written as r theta. And P doesn't necessarily have to be the letter P. It could be, any letter. It's just denoting that point specifically. An example of what this one would look like with numbers, you would see something like -2 and pi over 3. And we can have degrees. So the other option would be, 5 and 60 degrees or something like that. see. All right, they make a note here, which we'll have to see as we do examples, but it says, as in trigonometry, we measure theta as positive when moving counterclockwise and negative when moving, positive counterclockwise, negative when we're moving clockwise. So if r is greater than 0, p is on the terminal side of theta. If r is less than 0, then p is on the terminal side of theta plus pi. So those are those conversions that we had back in, like, whatever, but we don't need to write that down. We'll just do that when we get to examples. Let's see. All right, finding all polar coordinates of a point. Let P have polar coordinates r theta. Any other polar coordinate of P must be of the form r and then theta plus 2n pi, or negative r and theta plus 2n plus 1 pi, where n is any integer in particular. The pole has polar coordinates zero theta, where theta is any angle. Do any of y'all remember what the special name for our normal coordinates are when we do like x, y?
What letters start with?
R.
Radial?
Give you a hint, it's a shape.
Rectangle.
Rectangular coordinates.
Really?
Say rhombus. I'm confidently gonna say rhomboid.
Oh wait, it would be rhomboidal.
Rhomboidal.
That sounds so weird though.
All right, so we can convert between our Cartesian rectangular coordinates and polar coordinates and vice versa. So
What's Cartesian again?
it's just like our normal coordinate plane that we deal with.
Ah.
But we plot rectangular coordinates on our Cartesian axis. We'll be doing these on a polar axis when we do these graphs later. So coordinate conversion equations. This stuff actually is relatively easy, the equation conversion part. Let the point P have polar coordinates r theta and rectangular coordinates xy. So our conversion, x is equal to r cosine theta and y is equal to r sine theta, which makes sense because we're used to x and y, you know, cosine and sine respectively. R squared is equal to x squared plus y squared, which that's something we've done all the way back to when we were doing sine, cosine, tangent, and stuff, and where we're given, you know, x, y, and r. That was, we would write them in terms of that. So that's basically r is just the hypotenuse value, is what that's saying. And then tangent of theta is equal to y over x. So if we need the angle, that's how we can get the angle, depending on what they give us. And so with these different things, we can convert back and forth between polar and rectangular. So that'll be some of what they ask us to do, is doing the conversions and stuff. Let's see if there's anything else. Something to remember is that when converting from rectangular to polar, there are an infinite amount of possible polar coordinate pairs so we typically just pick one or two. I guess I should say possibilities. Okay, because every time we go around, right, every 360 degrees, we get the same value. And so that's why that's the case. So in some of their examples, they just have chosen like two of them that work. I'm guessing it's going to specify when we're converting. Maybe, I don't know. I'm not sure, but anyways. I think that's basically it. They do one things using the law of sines to actually solve almost like a word problem, but by like a graphing word problem with like points going and stuff like that. So, but we'll look at some of those examples tomorrow and then some out of the book. Probably spend a day or two on this since it's, you know, very new. We've never seen it before. I've done it, but it's been probably since high school. So it's been a hot minute, but anyways.